Okay, hey everybody. This is the supplemental video for week 2 of stats. We'll be finishing up all or most of the chapter 2 PowerPoint, and I'll have this posted on Blackboard. I'll also hand out physical copies on Tuesday in class. And we're just going to pick up where we left off from before. So in this past Tuesday's class, we talked about frequency distributions. So taking our raw data, massaging it into a tabular form, organizing it a little bit. Sometimes we might just want to stop here and present a frequency distribution as a descriptive statistic, but sometimes we want to take that frequency distribution and convert it into a graphical representation. So the most basic form of kind of graph that we can come up with is, I think, a histogram. We all have seen these before. We may have created them before. And all that this is just a graphical representation of the frequencies associated with each class. So we see our grade range data that we discussed quite a bit in class. We see that we had those 5 bins, those 5 classes for the frequency distribution, the catch-all category 0 to 59, the 59.5 to 69, 69.5 to 79, and so on, up to the 89.5 to 100. We grouped together several different outcomes, many different outcomes into each of these bins, because for a graphical technique, we really don't want to have like 200 separate classes, 200 separate categories, and have most of them just be 0 or no bar showing up, and every once in a while have just a single bar show up. That doesn't make a whole lot of sense. This is a much more reasonable way to treat this data, to kind of treat it as though it's continuous, group it together into, in this case, 5 bins. Somewhere between 5 and 10 or so bins is usually a pretty good number to shoot for. And we get a histogram that maybe tells us a little more about the class at a quick glance, how the class did on this exam. So how do we create a histogram? Well, we just have our classes and our frequencies. We see that the class 0 to 59 had frequency 5. We can look back in our notes and see that from the frequency distribution. So we draw a bar of height 5 and width that is constant. The next bar over, well, this class actually had frequency 0. We don't omit this. We don't, squish the bars together or anything like that. We just leave a space there. The next bar over, again, same width as the first 2 classes, but the height for this one is 6 units. There were 6 folks who scored in the 69.5 to 79 range. So that bar of the histogram gets height 6. Then 5, and then 9 for the 89.5 to 100 class. We'll see later on, when we see some issues that can come up with graphs, we'll see that histogram is actually quite nice, because when we scale the bar, we're only scaling one dimension. We have the same width for every bar. So by scaling only one dimension, only scaling the height, keeping the widths the same, that actually means that just kind of naturally our perception of this kind of graph is pretty much in line with what we would expect from the data, or if we had looked at the numbers themselves. So that's definitely a positive thing. My general recommendation whenever we're dealing with graphical techniques is kind of simpler is better. So we could do a histogram like this. We could do a histogram where the bars don't touch. I think some people call that a column chart. Histogram, bar chart, column chart, all pretty much mean the same thing. But anything that has this characteristic where we have bars whose either height, or perhaps we rotate this 90 degrees and we use bars of different widths, but the height or the width is related to the frequency, and then the other dimension is of constant thickness. So that's our trusty histogram. Here's an example of a histogram with where the bars aren't wide enough to touch. This was our survey response data, rating us 1 through 5 stars. 1 person rated 1 star, 3 rated 2 stars, and so on. So at a quick glance, we can see that most of our customers seem pretty happy, 4 or 5 stars, but maybe there are some customers we didn't do so great in providing them a service, so maybe we should look into that. Here's kind of a joke histogram, but this would be more of like maybe a bar chart, some people might call it, with the bars going horizontally. So the trustworthiness of information by file extension, TeX, PDF, CSV, and so on. TeX is kind of the typesetting language that a lot of math and physics and chemistry and stuff is written in. So, but this would be an example of kind of that sideways histogram, bar chart, whatever you would like to call it. Here is a graphic that I picked up. I thought it was a super nice graphic. We can see for each of the 50 states plus DC, each of them gets a histogram. Each of them gets a histogram consisting of 10 bars. Now, we might debate whether this is a histogram or not. If we look up here, we see that this is the year-over-year percent change in population. But we can see that it's certainly some type of a bar chart. It looks a little bit like a histogram. And nicely enough, the combination of the bars along with the coloring, darker red for higher growth and darker blue for greater amount of decline, actually brings our attention pretty quickly to a few different pieces of the graph. We see that places like DC, Florida, Georgia, places out in the west or southwest seem to have pretty nice sustained high growth rates. We see the same thing with Texas. Texas is kind of famous these days for having just a really booming economy and housing prices going crazy, all that kind of stuff. We see a couple of states like, say, Michigan or Rhode Island, where they had several years of slight decrease in population. We'd kind of generally expect a small increase in population over time. So that might be something interesting that we might want to look into. I wonder why those populations went down a little bit those years when surrounding populations seemed to be kind of flat or maybe just increasing slowly. And we also see down here, Louisiana, this picture was from a few years back. So this was the effect of Hurricane Katrina on New Orleans when it basically destroyed the whole city. And you see that same year, Texas got a bump, Georgia got a bump. So a lot of people moved to these other areas. But then as the recovery, kind of progressed forward, some people started moving back. It looks like they had a few good years of population increase after that, when people were kind of moving back into the area, rebuilding, that kind of thing. So something like a histogram we can combine with coloring, with some of these other tools and techniques that are even more available to us these days with computers and so on, make it a lot easier for us to do more complex things that can be very helpful, like these. Or we'll see later, if we get too much complexity, sometimes that can actually be a detriment. One little detail I want to point out is that really, if we're being careful, a histogram really is a graphical technique applied to classes versus frequencies. And technically here we really have kind of what we might call it time series graphs, because the independent variable here is time, as we're going across the x-axis, not really classes. But I think this is a nice demonstration of how something like a histogram or bar chart can be used very effectively. When you consider that this is over 500 data points plotted on here in a sense, and we can pick out a few really interesting things right away. That certainly, if we had those 500 numbers just sitting in front of us, I think it would be a lot harder to tease out this information that we just can see by looking at it. And this was just the zoomed in version in case anybody's on a phone or something and having a little bit of trouble seeing the graphic. The next technique is a line chart. The book and some of these stats authors come up with the craziest names for things. I don't know who decided to call this a frequency polygon, but I think that's what the book calls it, and some books call it that. in reality, everybody just calls it a line chart or a line graph. So what's the difference between this and a histogram? Well, again, we have our classes going across the horizontal axis. We have our frequencies going along the vertical axis. We have our 5 folks in the 0 to 59 class, 0 in the 59.5 to 69, and so on. But instead of putting a bar in each of these, above each of these classes, we just put a dot. We put a dot above 0 to 59 at height 5, a dot at height 0 in the 59.5 to 69 class, and so on. And then we just connect the dots with a line. Why might we want to use a line chart instead of, say, a histogram? Well, an example there might be if we, for some reason, suspect that nearby classes that are near to one another, are somehow inherently related. If I think that, that it's likely that if I know something about this class, then the next class is going to be very similar to that one, something like that. So this line chart kind of naturally feels like it ties together adjacent classes, where something like a histogram doesn't have that feeling. So is a line chart the best example to use for this grade data? Probably not. If I know the number of students who got, a C, that probably doesn't give me a whole lot of information about the number who got a B or a D. Here's an example for the science folks. This is for from a GC mass spec machine, so gas chromatography mass spectrometry machine. And basically what this machine does, a very interesting machine. If you're interested in science stuff, look up how it works. It's super cool. But basically what it does, you see at the bottom here, this M/Z, it sorts chemicals by mass to charge ratio. And what we see is that as it's going along, it's creating some bins related to, say a mass to charge ratio near 30 or near 35 or near 40, whatever. And as basically the machine is pushing these chemicals through some porous medium, it's a little bit hard for the chemicals to get through. They apply an electrical current that helps push the chemicals through. And then there's a detector that when the chemical passes the detector, it sees some intensity. So we see it looks like maybe time 43 here, there was a big spike in intensity. And maybe I shouldn't have said time 43, whatever, mass to charge unit 43. At unit 60 here, at class 60, there was another spike, not quite as big as the one at 43, but significant spike, maybe a little tiny spike here at 78 that the computer can kind of see, but it thinks that it's above noise. And so this is our output, this bunch of basically histograms for each of these classes representing different mass to charge ratios. We have a certain intensity, a certain something like frequency. And the computer would compare this picture against a library of pictures of known GCMS results from known chemicals. And the computer decided that this was the one that matched the best. The best. I think this is acetic acid. So like kind of a ketone, but it's basically the one of the main component in vinegar. So this is what acetic acid would look like if you run it through a GCMS. And here's a similar example from a GCMS. In this case, it's more related to the gas chromatography side of things, where we're looking at the retention time in minutes. And this is how many minutes it took each of these different sugars to make it through that porous medium and get to the part where it does the mass spectrometry. So this is kind of another example. It's a bit more like a line graph. In this example, we see more of the lines kind of going up and down more smoothly here. And in this last example, it was presented more like a histogram than a line graph. And again, on the science side of things, here's an example of of output from a Sanger sequencer, so a genetic sequencer. And again, if you're interested in science or medicine or biology, super interesting, look up how Sanger sequencers work. But basically it works kind of in a similar way to that GCMS machine. It kind of pushes the chunks of DNA through a porous medium, and based on how long it takes them to get through there, it knows how long that chunk of DNA was, and based on how long the chunk of DNA was and some other stuff related to like lasers hitting chemicals attached to the end of them and so on, it can tell what base is at that length into the gene. So we see actually a combination of 4 line graphs here. One blue that's related to cytosine, one red that's related to thiamine, a green that's related to adenine, and the black is related to guanine. So we see as we're going along, we get, a big peak in blue, and that's a cytosine call. The next peak is in red, that's a thiamine call, and so on. And that's how this Sanger sequencer kind of reads the sequence for that gene. So that's just a zoomed in version if you're on a smaller device. And here's what a whole page outlook might look like. Again, with the crazy words and ogive, I don't know anybody who's ever called it that, but just this is a line chart of cumulative frequencies. So if you remember, we talked about cumulative frequency distributions. And the idea here was we start with a bin on one end or the other of the frequency distribution. So in this case, the less than or equal to 59 bin had 5 folks in it. And then we consistently increase the size of the bin. So the less than or equal to 59, we turn that into less than or equal to 69, and that's our next data point that we're going to plot. So this includes all of the previous ones, plus potentially some more. In this case, there were no folks who got a D, so we just stay the same. One more bin over, we expand the bin again. We include the same folks from the first 2 classes, but potentially some more. So we had some folks who got a C. So we had 6 of those. So our point rises to 11 people who got a C or below. And then again to B. And once we get all the way to the right, we should have accounted for everybody. We should have expanded our bin to the maximum range. And we see that we do have 25 folks who got less than or equal to 100. So that kind of serves as a check that we didn't miss anybody, didn't double count anybody, that kind of thing. And you'll see if you play around in Excel that there are tons and tons of options for how these pictures look. Like here I have little diamonds at every point instead of dots, and I put a black border around the diamond just to make it look a little different. There are tons and tons of different choices you can make like this. Okay. Relative frequency graph. When we talked about frequency distributions, we also mentioned relative frequency distributions. We could present our frequency distribution using the actual numbers, the actual number of respondents who preferred soft drink A, B, C, D, E, or we could represent that as a percent. So the only difference is instead of using the frequencies on the vertical axis, we just use the proportions on the vertical axis. Otherwise, this is effectively the same as a histogram. And we talked over some of these advantages and disadvantages of relative frequencies in class. One of the big advantages is relative frequencies are on a 0 to 100% scale. And that can be a lot more intuitive to understand, especially if we have a really big sample and we have numbers in the tens of thousands or something. It's just, they're not numbers we're used to dealing with. It can be a little hard to interpret, but scaling everything to 0 to 100%, those are numbers that are of a size we work with all the time. The big disadvantage is we don't know the population size. If the graph is just presented like this, we don't know the population size. And again, there are some other examples in Excel where we could say, make a graph that looks like this, but then maybe on top of each of the bars, have Excel like overlay the actual number in each of those. So, we could have 7, 4, 5, 3, 6, like a 7 on this bar, a 4 on this bar, and so on going across here. So there are options like that that can mitigate some of those disadvantages. Okay, so next we'll discuss a little bit about distribution shapes. So when we have, say, a histogram or a line chart representing a distribution, representing a frequency distribution, what are some words that we can use to describe that histogram or line chart? So we have two slides here. The first three bell-shaped, bimodal, and uniform. And then the next two dealing with skewedness. So bell-shaped, we see the description is that it's symmetric. There's a peak in the middle and it tails off to the sides. So a bell-shaped distribution might look something like this. So there's a peak in the middle. It's symmetric in the sense if we flipped it over that axis where the peak is, it would look the same. And it tails off to the sides. In other words, as we get farther away from this peak in the middle, our frequencies go down dramatically. A bimodal distribution is going to have two peaks, so it might look something like this. And a uniform distribution is going to be straight across or flat, or all classes are about equally likely. So let's think of some examples of these different distributions. Let's start with uniform because that's kind of an easy one to think of. The classic example here is something like a die roll. We have a standard die, 1 through 6, come up approximately equally likely. If I rolled the die 100 times, counted the number of 1s, 2s, 3s, 4s, 5s, and 6s I got, I would get something like this. Right, my classes 1 through 6, my frequencies would be about the same height. The same thing with, the result from, say, a roulette wheel. We could say something like male versus female births. Those are going to be kind of roughly equal. So things like that. So quite often, these are things, these uniform distributions result from things that, humans have created and want to be very consistent, but not all the time, right? So like male and female births, things like that. Bell-shaped distributions, this one's bimodal, and this one's uniform. Bell-shaped distributions, the way we tend to get a bell-shaped distribution is if we average together lots of small influences on a certain variable. So something like maybe height or weight or IQ or something like that. These tend to be the results of lots of small influences contributing to an overall outcome. Now in height and weight, kind of interestingly, we have lots of small influences, but we tend to have one big influence, right? Male versus female. IQ is going to be kind of just lots of small influences across the board. No really, one huge influence. So IQs are going to be normally distributed, but if we said, height of males or weight of females, something like that, then we've kind of stratified out that one big influence and we've left just the kind of lots of small influences that are contributing, that are kind of averaging together to make, a person's height or weight or something like that. Now, if I just looked at, say, heights or weights of the whole population, I might expect to get something that's bimodal. And why would that be? Well, females tend to weigh less than males. So maybe there's going to be kind of a bell-shaped distribution for females and a bell-shaped distribution for males where their peaks are separated, and they kind of combine together to give this maybe bimodal distribution. We might see something like that in society if we looked at, our whole population combined. So that's kind of what I think of as a canonical example of a bimodal distribution, is when you have a bell-shaped distribution, and these kind of distributions come up all the time in nature. But where you have, say, one substantial factor that really makes a big difference, but then the rest of it is kind of just averaged together, an average together of a bunch of small factors. So we're going to see the big difference pushing the two peaks apart for those two different kind of subpopulations. But then within each of those subpopulations, we're going to see that nice kind of bell-shaped distribution. The bell-shaped distribution is sometimes also called the normal distribution. And we'll see a lot more about this in chapter 6. And the central limit theorem will really tell us why this happens, why it is when we average things together, they tend to look this way. And it's also sometimes called the Gaussian, after the mathematician Carl Friedrich Gauss. So next slide in distribution, shapes right versus left skewed. And this has to do with outliers. So what is an outlier? Well, an outlier is just kind of a data point that doesn't fit in with the rest of the data. So we might think, for instance, that we have most of the data here in this region, but maybe there's a very small chance of getting data way out here under the off to the right, but not really not really a similar tail pointing off to the left. So if we were to actually look at a histogram, what might this look like? This might look like basically all of our data over here, and then a couple of data points way off to the right that don't really seem to fit in with the rest of the data. So this will be right skewed. The direction of skewedness is the direction where the outliers are. And classic examples of right skewed data are things related to economics. So things like income, wealth or net worth, revenue for a business. There are, very few enormous businesses that have a ton of revenue, and lots of smaller or medium-sized businesses that have a moderate amount of revenue. And then things that kind of derive from these. So things like housing prices, right? Most houses are kind of a reasonable price, maybe, I don't know, say between $50,000 and $300,000, and maybe in the Pittsburgh area. But then occasionally you get a $2 million mansion, right? The right skewedness of things like income and net worth means that those folks are going to be looking for luxury goods, and that's going to kind of right skew some of these things like housing prices or cars, right? There's a few people drive Ferraris or Lamborghinis or something, but most people drive Fords or Chevys or Toyotas. And left skewed, just the opposite. Small chance of a very substantial left outlier, and most of the data being clustered around, this area, but small chance of an outlier far off to the left. And it basically just looks like if you took this right outlier histogram up here and just flipped it around. Right skewed distributions are a lot more common than left skewed distributions. But one example of a left skewed distribution, it's kind of the most memorable one that I've heard, is number of digits or fingers slash thumbs that a person has. So, right, like almost everybody has 10. We can, oh, that's trying to draw a straight line. So like almost everybody has 10. There's a small number of people who have polydactyly, who have maybe were born with 11 fingers, and even smaller number who were born with 12. This is probably not even a big enough disparity. There were some folks who have, lost a finger or two. There are some folks who have, lost a hand, or, either through infection or something, maybe lost both hands, who have 0 fingers slash thumbs. So this will be a left skewed distribution, right? The chance of getting a person with 0 or 5 fingers, say fingers slash thumbs, while still quite unlikely, it's much higher than the chance of getting somebody with 20 fingers or 15 fingers, right? So left skewed distributions, I found it kind of hard to come up with real examples that aren't just like, basically just negatives of these, essentially. But here's kind of an example. And as an aside, if we were to look at a distribution, look at a histogram, and try to decide whether we would call it right skewed or left skewed, that is very much a judgment call, right? And the same is true of these three as well. Like, how close does the histogram have to be to straight across the top to call it uniform? Well, that's a judgment call. Same with bell-shaped. How close does it have to be to call it bell-shaped? That's a judgment call. We'll actually examine bell-shaped more closely in chapter 6. So we'll look at some ways to try to more objectively determine whether we think a histogram or a frequency distribution or population is roughly bell-shaped. And we'll look a little more closely at skewedness when we get to chapter 3. Okay, some other types of graphs. So as I mentioned before, a time series graph. Here's an example from a previous textbook we used to use, where it lists major airline accidents. And this is essentially a histogram, but the horizontal axis is related to time. So really technically that US population change picture with the red and blue coloring, they were really time series graphs, but I was using the demonstrative point about histograms. But in this case, we see for each year, we have counted the number of airline accidents that year. So we have a frequency on the vertical axis, but time on the horizontal axis. Here's an example of a time series graph presented more as a line graph. This is from Gallup polls. They actually don't publish this anymore. This unemployment, underemployment, and payroll to population picture like this. At least I haven't been able to find it. I don't know. They might have put it behind a paywall or something, but I haven't been able to find it for several years now. But this is actually 3 different pieces of information on the same picture. So percentage of people who are unemployed down here, percentage of people who are underemployed, so who have a job, but maybe it's not in their, career field. Maybe it's not, maybe they lost a job as a manager and are kind of looking for a management job, but kind of took what they can get for the time being, something like that. So underemployed is an idea that we don't really hear about nearly as often as unemployed. And then this idea of payroll to population, just another metric, talking about kind of the health of the job market, the economy, those kind of things. One thing we want to be careful about with time series graphs is, well, it's usually the case that we kind of have to pick a start and end point. Maybe the end point is current, maybe that's what we just choose up till today or something as the end point, but we then have to pick a start point. And if you look at this picture, going from roughly 2007 to 2015 or so, versus this picture going from roughly 2009 to 2015 or so, they have they kind of tell a very different story, right? They have a very different look to them. One of them, it's like, oh, wow, that was a bad crash. The other one's like, oh, wow, the economy just, kept chugging along and making a nice steady increases for our shareholders. By the way, this is the S&P 500 that I've mentioned a couple of times before in class. Right, these two different graphs, just whether I start in 2007 or 2009, tell a very different story. So anytime you see somebody presenting a time series like this, or somewhere where they had to kind of pick their class limits, so to speak, or their beginning and end, it's always worth just kind of asking yourself, well, what if they had chosen a little differently, right? What if they had chosen their picture a little to start a little earlier, or start a little later, or end a little earlier, a little later? Would that have made me think something very different? Say this versus this. That's always a good thing to keep in the back of your mind. And the same goes for, say, chapter 3, when we're talking about numerical measures. If I represent to you a rate of return over these years, say an average annual rate of return, this number is going to not look nearly as nice as this number looks like, right? This is going to be a much higher average annual rate of return than this one. So again, it's for a similar reason, it's always good to think, okay, they had to pick the data set they were working with. What if they had chosen a little bit differently? Would that have substantially changed the descriptive statistic they're presenting to me? So here's kind of a joke time series graph. The odds that a word I type will start with some weird symbol. If anybody's programmed in C++ or Python, they pretty much use normal characters. But these other programming languages use all kind of crazy characters. And then of course, all of these, Twitter and tagging things and all of that use crazy characters. Another type of graph that falls into this category of other types of graphs, it's a pretty famous one, the pie graph. Does a great job of presenting very cleanly and very clearly relative frequencies. So if I look at this, this was a report that our IT folks used to send out to us over email. They would send it out, I think maybe once a month or so. But we can see here that, we got a ton of emails every day that came through the system. We get a bunch of spam and all these kind of things. But if I just look at these actual numbers, the frequencies, it's kind of hard to make heads or tails of this, especially because it's kind of like center aligned instead of right aligned. So the, units digits aren't above the other units digits, that kind of thing. But if I look at the frequencies over here, the relative frequencies, I can take a look down this list and see, oh, well, sorry. If I look at the frequencies at the bottom here, I was looking on the right, I can see spam high. So I guess really important, bad spam was about 30%, medium spam about 25%, blocked connections, which I guess is maybe somebody tried to go to a website that they're not supposed to or something, 25, 30%. So I can read through these percentages and, if that's not a bad thing to do. But if I wanted to put those in a pie graph, I can see at a really quick glance, I have 3 contributions that are about a quarter each. And then the remainder is split about evenly between 2 other contributions. So I see blocked connections, medium and high spam are about 25% each. And then I see my other 2, my legitimate, so these are the false positives, the things the spam filter said, hey, we think it's spam, and the person that was getting delivered to said, no, it's not spam, release it. or bulk messages, those are about half of the remaining 25 or so percent. And we can tell that very quickly on a pie chart. So here's an example of a pie graph that I think is likely to lead to more confusion in this context than clarity. So this was from a pollster, kind of like Gallup polls. They're Rasmussen polls, and they're regarded highly in the business, right? So this was a report that they were writing about the economy, and they published this graphic, and actually one more. So I don't know, like maybe it was an intern doing this, maybe it was somebody's first day on the job, but they published this graphic, and this seems to be very confusing because if I look at this, are you happy with your job as the title? I see lots of blue yeses on the left picture, but then I see very few blue yeses on the right picture. And that kind of makes me confused, right? But what's happening here? Are you happy with your job? Yes or no is the histogram. Are you worried about losing your job? Yes or no is the pie chart, right? So the yes is blue in both cases, but pretty clearly, most of the people who are happy with their job are not worried about losing their job, and vice versa. So if you're going to use a consistent color scheme, maybe it doesn't make so much sense to present under that same color scheme kind of two questions that kind of are natural opposites of one another, right? This is, in my mind, more confusing than informative. So I look at this, and instead of saying, oh, okay, yeah, that's clear at a quick glance, I can tell what's going on, I say, wait, I really need to dig down into this and see what exactly was the question being asked, what exactly is the histogram versus pie chart getting at here. One that I think is even worse than that, from the same, you can tell the same background, it's from the same report, is this one. We have a year from today, unemployment will be higher, presumably the maybe proportion of people in each of these three strata who agree with this statement. So blue is age 18 to 39, red is age 40 to 64, green is age 65 or more. But then over here, blue, red, and green, now they mean something different: better, worse, or the same. The job market is better, worse, or the same as, I guess, a year ago. And the different rings, the concentric rings, represent the different age groups. So again, there's just so much going on here, and it's so hard to pull all of this apart. And especially with these pie graphs, we have one pie graph in the middle here, but then it's kind of like I can't even compare the worses to one another because none of these lines really line up with one another nicely, right? So I can compare the betters directly to one another and the sames directly to one another. But in my mind, this is just way too complicated. There's just so much going on here that you would make a much clearer presentation that can get the information communicated more quickly and more effectively by just listing the numbers, right? The graphical technique is a detriment here rather than a benefit. So kind of a joke, the yellow is the percentage of the chart that resembles Pac-Man for the pie graph. So something that's getting more common these days, I shouldn't say these days, but with more computing power, we can do things that would previously be very tedious. And one example of those kind of things is heat maps. The idea of a heat map is really that idea that we saw in the annual population growth chart from before, where we looked at all of those different states, and the higher population growths were deeper red, and the higher population declines were deeper blue. Similar kind of idea with a heat map. Here's an example of a heat map analyzing monopoly. So using payback periods, so number of opponent rolls that it will take you to, on average, recoup your investment in a property or house or hotel or whatever. So we see that a higher number of opponent rolls is a worse investment, right? It takes a longer amount of time for me to pay off that property. So something like Mediterranean or Baltic, buying the single property takes 1,000 opponent rolls to pay off. Maybe I'll, avoid that investment. If I look at where the deeper red, say deeper orange, deeper red are, the lower number of opponent rolls to pay off, the properties that pay back faster, that are going to be more lucrative. I see they're kind of over here in the third house and fourth house. And I see that, St. James, Tennessee, New York, that seems pretty nice because it's not too terrible for a single property or the last one on the block. But then that'll give me access to some of these really nice opportunities over here on the right. Also, the railroads, even the first railroad isn't a terrible investment, but once you get to the third or fourth, they're very good investments. Only for the fourth railroad, only 13 opponent rolls to pay that off. On average, of course, right? And I can see that by just glancing at this picture, right? I can see that this black border here, and these are the kind of nicest payoffs. This is an example of the Index of Economic Freedom from the Heritage Foundation, just looking at some economics data and how free, in a sense, each country is with their economy and policies and those kind of things. And again, we can see heat maps. Or we can see a heat map here. We can see darker red for countries that have lower economic freedom, that are lower on this index. We can see darker green, or I guess green in general. There aren't too many countries that are very dark green, but this green color, the lighter green, is kind of the relatively high economic freedom countries. And so if we were interested in, whether countries tend to cluster a certain way or something like that geographically, a heat map might be the way to go for something like that. Another example is in the US, annual mean wage of registered nurses. This was from 2021. This is from the Bureau of Labor Statistics. And we see that the darker blue in this case represents higher wages and the lighter blue represents lower wages. So I see that places like Alaska, Hawaii, and the coasts tend to pay higher wages, and kind of the Midwest in here tends to pay lower wages to nurses. So one caveat to this is there's also a cost of living issue, right? Costs a lot of money to live in Alaska or Hawaii, where basically everything you need has to be flown in. Costs more to live in, say, California or Washington or New York. Housing prices are higher, just general prices of things are higher in those states. And it's pretty affordable to live in, Kansas or Oklahoma or something. Cost of living is much lower there. So that might be something that we'd want to keep in mind if you've got a couple job offers from a couple different states. Maybe keep that in mind. What's the cost of living? Not just how much are they going to pay me, but also what's the cost of living. And then, of course, do you like the company and all of that too? All of that's very important as well. Okay, so the next bit is on scatter plots, and scatter plots were kind of shifting. We're shifting perspectives here a little bit. So before we had one variable, say something like grades, and we had different classes. And the vertical axis was always something like frequency or relative frequency, something like that. So we're looking at a single variable, data from a single variable, and plotting it on this two-dimensional graph, where one of the axes was directly related to that variable, and the other axis was kind of just a counting number. Scatter plots are different though, because scatter plots are looking at two variables. So what's the idea of a scatter plot? The classical example of data you might plot on a scatter plot is heights versus weights. So say we have a bunch of people and we gather a list of heights and a list of weights from those people, from that sample, let's say, and we want to plot them on a scatter plot. Now, the thing to realize is that it's not just like I have a list of heights and a list of weights and that's it, but it's actually kind of a paired list, right? So person number one, we measure their height, we measure their weight, and these are paired together. Person number two has a certain height and a certain weight. Those are paired together. So a certain height and a certain weight belong to the same person. So I could think of this as an ordered pair from just kind of our basic, algebra and geometry and so on. And I could think of this in the sense of like a Cartesian coordinate system, like a two-dimensional graph. And I could say maybe person one, they can be represented by this point, by this height and that weight. So that is person one's data point. Maybe person two is over here, person three is over here. So each different person gives rise to an X value and a Y value, and each different individual person, each different individual data point is going to be a dot over here. So maybe I get something like this as my scatter plot. My scatter plot is inherently comparing two variables. In this case, height and weight, or just any two variables, X and Y. Typically, I'm looking at a scatter plot to try to tease out if there's a relationship between these two variables. These scatter plot examples over here are from a medical process called flow cytometry. So basically what they do is they take your cells are not really smooth. They're like kind of almost like hairy, you might call it. They have all these little proteins hanging off of them that do all kinds of important things. And you can attach an antibody to certain proteins that will fluoresce a certain way when it's hit with laser light. And they have a tube with a laser that points into it, and they literally flow cells through one by one through this tube, through a liquid medium. The cells go down, the laser hits them. There's a measuring device on the other side that sees what intensity of what different colors of light is coming off of the cell, and that tells them what's the intensity of, say, CD34, cluster of differentiation 34, just the 34th thing of interest that they've made an antibody that attaches to and has a fluorophore at the end. Or what about CD19? And a pathologist, maybe an oncologist, will look at these pictures like this. Each one of these little tiny dots here is a different cell, and they'll say, oh, there's a lot of cells around 10 to the 0 is 1 and 10 to the 1 is 10. So between, say, roughly 0 to 10 units of intensity on CD34, and between 0 and 10 units of intensity on CD19. And maybe that means something really important to them, that this person, they think, maybe has this disease or does not have that disease. Or the same thing with the CD34 versus CD13 down here on the left. We see a lot of a cluster of cells in this kind of area here, right around, say, 100 units of intensity related to CD13, and 100 to 1,000 of CD34. Maybe that means something to somebody who's trained to read these. Here's another example that kind of incorporates a little bit of the heat map idea. If we look up here, if you look at, say, this top left chart here, there's just a ton of data down in this bottom left corner. but there's so much that the points just kind of like sit on top of one another. And once that area has turned black, I don't know how many points there are, right? But this example here, the more points there are close together, they actually turn it, blue, then green, then yellow, then red. So they use a heat map idea to represent the idea of kind of the intensity or the density maybe of points in that area, giving you a little more information still. So you see where the clusters are, and you also see the intensity in those areas that where it would otherwise just look like a big smudge. So this is CD4, CD8, and CD3 cells. These are markers. These are related to immune cells. So again, if you're interested in medicine or biology or something, look up flow cytometry, another super interesting science topic. Here's an example of a scatter plot that I pulled out of the Stanton Glantz book, or it's really not from the book, it's from it. He analyzes it in the book, but it's from a paper in the Annals of Rheumatologic Disease. And what they're trying to get at here is some folks have rheumatoid arthritis, some folks don't. How does rheumatoid arthritis affect grip strength? Grip strength is super important for all kinds of things, to maintain independence as you get older. So just being able to pick up things, but also like if you need to grab something and pull yourself up either off the floor or from a seated position or something, being able to do that by yourself is quite important. So this is a really big deal, for a lot of people getting older. So they have a scatter plot here where we see that we have the cross-sectional area of muscle across the horizontal axis and grip strength in newtons along the vertical axis. We're comparing these two variables, and each one of these little points here is a different person that they studied. Say this person here has something like 30 square centimeters of cross-sectional area of, I guess, forearm muscle. And they have, maybe it looks like 75 or so newtons of grip strength. And they do that for all these different people. And interestingly, they've also stratified these folks, right? The normal subjects have a triangle. So kind of on the top right here, you see lots of triangles. And the RA folks are indicated with a diamond. So kind of on the bottom here, you see more of the diamonds. So that's what this scatter plot represents. And then these two lines, one thing we can do with the scatter plot is we can say, it's kind of complicated to look at all this data. Can I come up with a model? Can I come up with a linear model? Lines are pretty simple. Can I come up with a line that kind of is pretty close to most of the data points, that does a good job of modeling this data? And in this case, the question is, what impact does RA have on a person's ability to exert strength through their grip? And we can see that as cross-sectional area increases, strength increases, as we'd expect. But for the RA folks, they're modeled by this bottom line, where the normal folks, the non-RA folks, are represented by the top line. So we can see that for each additional square centimeter of muscle mass, the non-RA folks get a much bigger benefit to strength than the folks with RA. So, having RA is going to be a pretty significant thing for these folks to deal with. That's going to severely impact their strength and their ability to maintain independence. I think log, and semi-log plots maybe we'll leave until Tuesday. So we'll leave that until next week. We'll kind of go through these. And I think we'll wrap up today with maybe misleading graphs. So a few different ways to mislead using graphs. And at the end of chapter 1, we talked about misleading statistics, and the same ideas apply here. If you see somebody present a misleading graph, it's not necessarily that they're acting out of malevolence. It could just be they just didn't do a great job that time creating that graph, and vice versa. If you see something presented by somebody that you think is a highly ethical and honest person, that doesn't mean that it's correct. They might have made a mistake. So always good to just think about these things when you see a graph and just ask yourself these questions regardless of the source. So the first is, if we're evaluating something like revenue of, let's say, Apple versus Microsoft, I could present a histogram like this, right? A amount of revenue for Apple versus Microsoft. And I mean, I suppose this isn't wrong. Apple had something like 65 billion in revenue, and Microsoft had something like 70 billion in revenue. But if you just look at this picture, right, if you're not careful and if you don't carefully look at the scale over here, this picture can be very misleading. It can make it seem like Microsoft has, 50 times the revenue of Apple, and that's just not the case. We know that revenue is ratio data. So again, this is where these ideas of discrete versus continuous variables or measurement scales come into play. We know that ratio data has a true zero. We probably should respect that in our graphical techniques. We should just start the bars at zero so that we maintain those ratios, so that, if a bar is twice as high, then it looks like there's twice as much revenue and everything is, consistent, right? Up here, it seems we might be tempted to think something like, well, this bar is, I don't know, 10 or 20 times or something as tall as that bar. So I'm guessing that they have 10 or 20 times the amount of revenue. That might be our natural inclination. So this kind of a picture is going to be much better, starting at zero, because there is a true zero here. Zero revenue means they didn't make any money. Here's another example, top 10 most read books in the world. And if we look at this, we would say, oh, well, kind of everything from Anne Frank to Lord of the Rings is about the same. Harry Potter, a little bit more. Mao Zedong, a little bit more. And then the Bible maybe twice as much as Mao. But really, if we look at the actual numbers associated with each of these, it's like, 27, 30, 60, 100, then to 400. Harry Potter's 4 times as much as Lord of the Rings. Mao is twice Harry Potter. And the Bible at 3,900 is like, something like 4 or 5 times Mao. Well, what they're doing is that they actually did kind of the opposite. Instead of, burying the zero way below the graph, they kind of did this little cute thing where they have the spines of the books there, and they set the zero at kind of just above the title. But it has the appearance that the bar starts down at the shelf, but really the kind of histogram part of the bar starts above the title at this zero. Now they did put the numbers here. So, I mean, fair enough. It's not like they're, trying to be deceptive or something. But if I have to look at a picture, say, oh, I get an idea from that picture, and then I read the numbers, and I get confused, and I say, wait, that's not consistent with my idea. So then I have to read the numbers and see what all the numbers say. Well, that's no better than just presenting the numbers alone in the first place, right? So we should be careful with these graphical techniques. Another issue is perception. We tend to perceive areas more than linear scales. So if I were to say something like, I doubled my sales from, 1 year to the next, and I increased the, say, dimension of the diameter of this circle by a factor of 2, well, really, I've increased the area by a factor of 4, and it's going to, the comparison is going to make it seem like I have 4 times the amount of sales rather than 2 times. So something else that warrants mentioning that we've mentioned previously, things like detection bias, inconsistent units, etc., that pop up so often in time series. Time series analysis is it's kind of its own animal. There you could take a stats course, you could take many stats courses just in analyzing time series. There are all kinds of things to watch out for, and little things that can bite you in time series, so you have to be careful about. It's one of the things that makes finance kind of interesting. Is in finance we use time series all the time, so the stats are a little more complex than in some other places. But here's an example from kind of the medical field. So this was also from a previous textbook we used to use. Leading causes of death for men 25 to 44 years old, going from 84 to 94. Now, if I just look at this, I might think, okay, well, obviously the big standout is HIV, going from 84 to 94 is killing a lot more people. But it seems like cancer is also killing more people, where it looks like heart disease and strokes may be about the same, and heart disease leading to fewer deaths. And it seems like accidents have gone down dramatically, right? So one way that we might look at this, we might say, oh, well, we have a lot more people getting cancer. Are we like doing something to get more cancer at a young age? But the other way that we might interpret this is, remember that lead time bias issue, right? It's kind of related to that. It's a detection bias issue. In other words, if somebody died of some obscure cancer in 1984, maybe they're just chalked up as died of natural causes. We're not really sure why. They got some infection and just ended up dying. But in 94, maybe we're better at detecting that cancer. Maybe over that 10 years, it could have been that we got better at treating the cancers and people were getting less cancer overall, maybe, but maybe we just got a whole lot better at detecting them. Our imaging and so on, and blood tests and all of that got better. That could be, right? Is there a detection bias for accidents if somebody is killed in a manufacturing accident or something? No, not really, right? If somebody is killed in an accident like that, it's pretty easy to detect and say, yep, we can attribute that to an accident. And, we can be pretty confident in that number. But over this time period, the US for many decades now has been moving away from things like manufacturing and heavy industry and towards things like service. So that accidents number does make sense, that it's going down. And heart disease and strokes, maybe I don't think there's much of a detection bias there. I mean, it's usually pretty obvious with the symptoms if somebody has a stroke or a heart attack, something like that. So, those we see pretty much flat. So maybe there's less detection bias, but maybe we're getting a little unhealthier because we have sedentary lifestyles, living in office or working in offices and things. But maybe we're also getting a little better at treating them. So it's kind of just equaling out. HIV from 84 to 94. Well, is this an increase in the actual number of people dying from it? Is it an increase in recognition of it and people being willing to talk about it, being willing to go and get tested? Is it an increase in detection? There being better tests that are more accurate? Is it maybe all of those things combined? That would be an interesting question for, say, a public health person to look into or consider. Another example of a misleading graph. This is from a very well regarded textbook, Robbins Pathology. So I saw this picture, and this is something like I think it's something like the risk of a cardiac event, risk of a heart attack, basically 5-year risk for each of these populations for people who are non-diabetic with no prior heart attack, above a certain age, people who had no prior heart attack but are diabetic, people who had a prior heart attack but are not diabetic, and people who had a prior heart attack and are diabetic. But then I saw the numbers listed and it said non-diabetics, no prior MI is 2 units of risk. I forget what the units are. But over here, if you look at this leftmost bar, it looks like it aligns to 0. It doesn't look like 2. And that like befuddled me until I looked. If you look kind of on the right sides of these bars, there's this kind of gap between the bar and the background, right? The bars aren't pushed directly against the background. And we're looking at these 3-dimensional bars from the top right. We're actually getting a parallax effect here. So if you ever looked, like at a clock from the side or something like that, it can be sometimes hard to tell what minute it's on. You want to look at it straight ahead. Same kind of thing here. Trying to get too fancy with the graphs, and they get a graph like this, you can go in and you can manipulate it and there's an option in Excel called gap depth. You can set it to 0, and that pushes those bars against that back wall. And now that, non-diabetics, no prior MI risk at 2 units of risk, it's more sensible. It looks better. But I think it's even better. Just use a 2D histogram, right? There's no reason to use fancy 3-dimensional things. Again, it just increases the complexity, and in this case, is detrimental. It misrepresents the actual numbers. Okay. I will say, it doesn't affect the qualitative point that non-diabetics with no prior MI are quite low risk for a heart attack in the near future. Whether if you had one or the other, prior heart attack or diabetic, but not both, you're at a substantially higher risk, but about an equal risk. And if you have both, you're at a much, much higher risk. So did it affect the qualitative the qualitative information coming across? Probably not. But could it have been done better with just the 2D histogram? I think so. These are the sources, and that wraps up our discussion for chapter 2. So when we come back in class on Tuesday, we'll talk a little bit about log, and semi-log plots. We'll talk about how to create some of these graphs on Excel or by hand, and then we'll move on to chapter 3.